Okay, so here we're going to go over the notes for chemical nomenclature. This is in class session 4, and so you should look over that, read through the notes, and then I'm going to go over most of the notes and problems in these videos. The first slide is a review from the last section, class session 3, and it talks about metals and nonmetals. The only nonmetal over here is hydrogen. Everything else is a metal, and then you can't see it in black and white, but there's this stair step that starts right there and cuts off the metals from the nonmetals. So everything over here is a nonmetal, everything else is a metal. So this is what helps you predict ionic compounds or molecular compounds. If you have a metal, it's an ionic compound, and you always have the metal plus the nonmetal. The metal is written first, nonmetal is written second. If you have a molecular compound, that's between two nonmetals, so it's between all of these or hydrogen. So you can see that the bulk of the periodic table is metals. However, these nonmetals can combine in a large, vast variety of ways to form a lot of different molecular compounds. But there's a lot of metals to choose from in forming ionic compounds, and so there's a lot of different ways that they can combine, and we need to distinguish them by naming them. So here on the periodic table, if I were to figure out where metals and nonmetals are, this is hydrogen, that is a nonmetal, everything else is a metal. I'm going to start this stair step between boron and aluminum. In this region we've got metalloids, but for the purposes of this we're just going to break it up into metals and nonmetals, and so it's a close enough assumption that these are metals, these are nonmetals. When we write ionic compounds, the cation is always written first. That's going to be the metal. The resulting compound has to be neutral. That's the key to figuring out charges. The subscripts must be in simplest form. And so we use the swap-flop rule, which is talking about the charges. And so here we've got magnesium 2, chloride, that's an understood 1. And so if you swap those, it's magnesium 1, Cl2. So that 2 is there. And the reason this works is because you want it to be neutral. So if magnesium has a 2 plus charge, then what we want is 2 negative charges for chlorine. So you've got -2 and +2 in this compound. So you want it to be neutral. Aluminum 3 plus, oxygen 2 minus, swap them, Al2O3. Barium and oxygen, swap them, but you want to simplify it. So it's really, you'd have 2 and 2, and then you simplify it to be 1 and 1. Or you can just look at the fact that they're equal, and so you only need one of each one in order to make a neutral compound. So one of that makes a neutral compound. Here you can see that it's neutral because you've got 2 aluminums at 3 plus, so that would be +6. 3 oxygens at -2, -6, and so you have a neutral compound. For metal cations, we have 2 different kinds. We've got kinds that always form the same cation. And so groups 1, 2, and 3 always form that cation. Type 2 are metals that can form 2 or more cations with different charges. So these are the transition metals where they have variable charges. You can't actually predict them looking at the periodic table. Also, tin and lead, they also form compounds with variable charges. So they're right here, tin and lead They're in the metals, but they're close to the transition metals, and they can either be +2 or +4. And so, whereas these, we can look at them and know what the charge is, we can't with the type 2 metal cations. And so we have to name them differently when we're talking about naming ionic compounds. When we name the type 1 cations, it's simple. We just take the name of the metal and add cation at the end. So you have K+, potassium cation, magnesium, magnesium cation. So you find all these names on the periodic table, potassium, so just potassium cation. And we don't have to indicate anything about the charge because you can get the charge by looking at the periodic table. Groups 1, 2, and 3. Everything in this group is +1. Here is +2, and this would be +3. And so you can tell that from the periodic table. When you name the anions, you're going to replace the end of the element name with "ide," and then you're going to add anion at the end. And so fluorine is going to become fluoride. Nitrogen would become nitride. And so they take out the little OG just because it sounds better, so it's nitrogen, becomes nitride. Sulfur, sulfide. Bromine would be bromide, and so we're just adding "ide" at the end. And then if it's just the anion we name, just add the anion. And so here are some common simple cations and anions. And you look at how those are changed. So here we're just taking the name. Anions, you're always going to have this ending change. So when we're naming ionic compounds, the name of the cation comes first, and then the name of the anion second. And so these are the simple ones with groups 1, 2, or 3 metals, type 1 cations. And so NaF, sodium fluoride, LiCl, lithium chloride, Ki, potassium iodide, MgCl2, magnesium chloride. So here, if we want to name the following binary ionic compounds indicated by the following formulas. And so here we've got Ki, and we just saw that earlier. That's potassium iodide. So we've got iodine, we change the ending to "ide." MgCl2, that's magnesium. And this is from chlorine. We'll change the ending to "ide." Magnesium chloride. Na2S, sodium. And then we've got sulfur that becomes sulfide. Al2S3, aluminum. And then the S is sulfide. Aln, aluminum again. And then the ending is nitride. So, name of the cation, straight from the periodic table. The anion, you're going to change the ending like that. Turn it to "ide." So type 2 cations are transition metals and metals of group 4A, which is tin and lead. They have variable charges. Different cations of the same metal form different compounds. And so because of that, we can't just say lead oxide for this. And the reason is because they're both lead oxide. So how would we tell which one it is? If we're looking at these, there's only one potassium iodide, one magnesium chloride, only one sodium sulfide, etc. But there are 2 lead oxides. And so when we're naming type 2 cations, we have to indicate what kind of lead oxide we have. And so when we're doing this, naming type 2 cations, we keep the name of the element, then we indicate the charge with a Roman numeral. Roman numerals would be 1, 2, 3, 4. And usually that's all we really go up to. But here, so iron 2 plus versus iron 3 plus would be iron 2 or iron 3. And so we have to indicate what that is when we are naming the cations and naming the compounds. Here are some examples. These used to be the older names here. I'm not going to make you learn that, but you can look at how what they used to do is for the higher charge, they would add "ic." The lower charge, we'd add "us." And then they would use the Latin names. And so for iron 3, it would be ferric, iron 2, ferrous, copper 2, cupric, copper 1, cuprous. So you can look at those, but this is what I want you to know how to do. And so here you can see iron 3 plus is iron 3, iron 2. All we're doing is taking the name of the cation and then in Roman numerals putting whatever that charge is there. So the charge is in Roman numerals for tin 4 plus, put the 4 right there. So when we're putting these compounds together, if you have copper chloride, it's going to be copper chloride, but we need to indicate what the charge is. This is where it can get a little tricky because we have to figure out what that is. If we're just given CuCl2, well, we've got copper, and we've got 2 chlorines that have a -1 charge. And so in order to make a neutral compound, what does copper have to have? You've got 2 -1 charges here, so that's a -2. We've got 1 copper, so it's got to be +2. And so we have to go work backwards to figure out what copper's charge is. So here we have copper 2 chloride. More examples, copper bromide. Here, bromine has a -1 charge. And so we've got 1 bromine or 1 bromide. And so copper has to be +1 in that. And so it's copper 1 bromide. FeS. This can be tricky because you can think, oh, it's just iron 1. But sulfur is -2. And so if you have 1 sulfur and 1 iron, iron has to be +2. Lead oxide, here's another tricky one because lead O2, it'd be really easy to say that that's +2. But oxygen has a -2 charge, and how many of them are there? And so if you've got 2 -2 charges, that's -4. Lead has to be +4 in order to make that neutral. So here you can see that they set it up like an algebra equation. You can make X the charge of the lead ion, plus you've got 2 oxygens that are -2 charge. That has to equal 0. So this always has to equal 0. And so if it's a -4 equals 0, so X has to equal 4, +4. And so that's lead 4 oxide. This is going to be the trickier part of naming ionic compounds, when you have to work backwards and figure out what the charge is. Here we want to write the formula and give the name for the compounds. So these are a bit easier because they're giving us the ions, so then we know what the charge is. And so when we put this together, we've got CuBr2, and that's going to be copper. The charge is 2 bromide. Here we've got iron 2 plus, oxygen 2 minus. We just need 1 of each. And so this is iron oxide, but I need to put the charge. It's 2. Lead +2 and chloride minus 1, so PbCl2. Notice that the anions never have variable charges. You never have to worry about that. They're always going to be the same, and it's always going to be either the minus 1 for this, minus 2 right here, or minus 3 in this group. Carbon very rarely forms an ion, and so we're not going to really deal with that. It forms molecules or covalent bonds, which we'll talk about later. So this is the main thing you need to remember, what these anions are, because that's going to be what you plug into your equation to figure out these variable charges over there. So here we've got lead to chloride. All of these are 2. Here again, this is like B. It's just HgS. And Hg is mercury, 2 sulfide. Okay, now here's where we get the trickier ones. Give the names for the following compounds. So, the easy part is saying that this is some form of copper oxide, but we don't know what it is. We know that it's going to be a type 2 cation because it's not one of the ones in group 1, 2, or 3, or tin or lead. It's a transition metal. It's right here. We don't know what the charge is. You can't predict it just by looking at that. And so here, oxygen is minus 2, and we have 1 of them. So copper has to be then plus 2. And so this is copper 2 oxide. Here, we've got cobalt fluoride, but we don't know what kind of cobalt we have. Fluoride is in this group here. It's a minus 1. We've got 3 of them. And so if you've got a minus 3, X plus that minus 3 has to equal 0. And so cobalt has to be plus 3 right there, cobalt 3 fluoride. Same thing right here. Iodine is also a minus 1 because it's right there in the minus 1 group. And so we've got minus 4 there. X plus a minus 4. Tin has to be 4. And so we've got tin, 4, iodide. FeS, this is one where you've got sulfur, which is a minus 2. So they're pretty straightforward if it's a minus 1, but when you have the minus 2, it could be canceling out. And so here, that has to be plus 2. We've got iron, 2 sulfide. So, when we are naming a compound, you're going to first ask, does it contain type 1 or type 2 cations? Type 1, 1, 2, 3, right there. Group 1, group 2, or 3. Type 2 would be anything in the transition metals, tin or lead. If it's type 1, just name the cation using the element name. No Roman numerals needed. If it's type 2, using the principle of charge balance, determine the cation charge. And then include the cation name and a Roman numeral indicating the charge after that. So this is going to be really helpful when you're determining how you name it. So here are some examples where here you've got, what kind of cation do you have? It's a type 1 cation, it's aluminum. It always forms aluminum plus 3, so there's no need for a Roman numeral. Chloride, the anions will never be variable. It always forms Cl-, so it's just aluminum chloride. Here, Fe2O3, the cation is type 2. It's a transition metal. And so we have to figure out what the ion present is. It's plus 3. And the reason here is because you've got 2 irons plus 3 oxygens that have a -2 charge, and that has to equal 0. And so this is -6, that has to equal 0. So 2 irons plus a -6. If you move that over, divide by 2, it has to be +3. So you have to do some simple algebra to figure out what the ion is, what the charge is, and so you're going to have to name it using that Roman numeral. So these are the ones that can be the trickiest when you are trying to figure out what the charge is. Okay, I'm going to stop here. I'll make another video to go over the rest of the notes. Probably have 1 or 2 more videos, but stop here and go over some practice problems and rewatch this video. Always email me if you have any questions. Okay, so the rest of the notes, we'll try to get through this in one video. Here we're just introducing the concept of what's called polyatomic ions. These are ions, but they're covalent compounds. And so we haven't talked a lot about covalent compounds, but we will. Covalent compounds are, like we talked about before, nonmetals. And so covalent compounds are 2 nonmetals. And so here, if you look inside here, you've got nonmetals. You've got nitrogen and hydrogen and oxygen and sulfur and phosphorus. But as a whole, they carry a charge. And so the whole group carries a charge. So they're actually ions. And so it's basically like if we had sulfur, that's 2 minus, or sulfide, it's similar to sulfate, which as a whole carries a 2 minus charge. And so we're going to put them in ionic compounds, or they form ionic compounds, similar ways that regular anions do. Here are some polyatomic ions. These are the ones that I want you to memorize for the midterm. And when we get to the midterm, I'll remind you about this and give you some flashcards to study from. But these are the ones that are most common, and so it's good to be familiar with them. If you do enough practice problems, you will eventually become familiar with these because these are really common. Ammonium is the only positive polyatomic ion. Or at least the one that we're going to use most regularly, the only positive one. The rest are negative. They contain, almost all of them contain oxygen, with the exception of ammonium. And then they contain some other nonmetal, and they will sometimes also contain hydrogen, but different numbers of oxygen. And so you have here 4 different chlorine compounds, all with different numbers of oxygen. And so the way they've named them is hypochlorite, chlorite, chlorate, perchlorate. And so that is the naming system, and we just use these when we are naming ionic compounds. So for example, if you have NaNO3, now when you see this you might get confused and think, so I have sodium and nitrogen and oxygen, how do I name that? And so it's important to be able to recognize these polyatomic ions. If you see a metal, then whatever's after it is all going to be part of this polyatomic ion. And so you've got this metal, which is sodium, and then anything after that metal, NO3, is going to be the polyatomic ion. And so if you look at the chart, NO3 is right here, and it's got a -1 charge. And so that's NO3 minus. Here, ammonium's the only one that's going to be first, that's not a metal. So it's the only ionic compound that's not technically metal plus nonmetal, because you have this ion that's functioning like a cation, functioning like a metal cation, but it's made up of nonmetal. So here's ammonium, and then chlorine, it's anion form, so ammonium chloride. Here's another tricky one. Got ammonium, and then you've got acetate. This is like acetic acid or vinegar. And so here you've got 2 polyatomic ions. It looks really confusing, but really you just have 2 polyatomic ions. You just name it straight from the chart. And so once you recognize that it's a polyatomic ion, you have, okay, I have ammonium, and then I've got acetate, which is written right there, C2H3O2. And so ammonium acetate, put that together, and you've named the ionic compound. So if something looks really confusing, more likely than not it contains a polyatomic ion. You need to look at the chart, and it's going to be much simpler than it initially looks. So, writing these formulas, here we've got a mixture. We've got some just regular anions, we've got some polyatomic anions, we've got some type 1 cations, and we've got some type 2 cations. So here, sodium iodide, we've got sodium, which is in group 1, so it's a +1. Sodium is right here, +1. And then we've got iodide, which is in group 7. It's a -1. And so when you put this together, you get NaI. Then B, we've got calcium chloride. Calcium is +2. Chloride is -1. Getting these from the periodic table, calcium's right here, chloride's right here, and so +2, -1. Put those together, CaCl2. C, I'm gonna run out of room, I'll get another piece of paper. And potassium sulfide, so potassium is K +1. Sulfide, sulfur, and it's in the -2 group, so -2. Put those together, do the swap flop, K2S. D, lithium nitrate. Lithium is in the +1 group, nitrate. And so here you might think, oh, it's nitrogen, but that ends with "ide." If it ends in ate or ite, it's going to come from this chart. So if you look at these, a lot of them end in ate or ite. There's only a couple ides that can get confusing: hydroxide, peroxide. So you want to be familiar with this enough to know this isn't from the periodic table, this is a polyatomic ion. But the rest of them you can tell because of ate or ite. And so which one is this? We've got lithium nitrate is NO3-. So once you figure it out, you're given the charge, and so you just have to write the formula. +1, -1, we've just got one. And so now we have copper sulfate. That's copper. And they tell us what the charge is. So copper's here. We couldn't figure out the charge from there, but we've got a Roman numeral. Sulfate, we're going to look right here, and that's SO42-. And so put those together. Those neutralize each other with just one of each. So we've got CuSO4. Sodium carbonate, Na+1. Carbonate comes from here, CO3 2-. Either way you write it, 2-, -2, either way is fine. So here, swap flop, that 2- is going to be right The 2 is going to go there, and then you've got CO3. G, got calcium nitrite. And so if you look at the chart, nitrite is NO2 minus. Put those together. Ca, when you've got more than one of the polyatomic ion, you have to put it in parentheses so you can indicate the 2 there. Otherwise, you wouldn't be able to put that 2. So you need to put that in parentheses if you have more than one. H, potassium perchlorate. CK plus perchlorate is this one with the most number of oxygens, 4 oxygens. ClO4 minus, 1 of each. ClO4, like that. Here, this next one we want to give the name. And so we've got silver oxide here, but we don't know what the charge is on silver because that is a transition metal. So you want to figure out what the charge is. So that 2 is there because of the oxygen. And so we've got 2 silvers. And we've got 1 oxygen, which we know is a -2, and that has to equal 0. So here we're just going to do some algebra. 2 silvers minus 2 equals 0, plus 2 plus 2. 2 silvers equals 2, and so silver is plus 1. You can get that by dividing by 2. And you can do that. You can do it in your head. Just get to the fact that silver is plus 1. And so when I name it, silver 1 oxide. Here, calcium is a type 1 cation, so we can just name it calcium. Here, it's a polyatomic ion, OH minus, and it's hydroxide. So all you have to do once you find it is just write hydroxide. Here, we've got potassium, type 1. This, if you look at the chart, ClO3, chlorate, so potassium chlorate. Here, so when we went over before, you've got 2 polyatomic ions. It looks really confusing, but it's really just ammonium hydroxide. So when you're naming it, it's from the chart, you're just looking straight at the chart. It's easier than it looks because you just have to copy the names. Here, CrO4 and then iron. So we've got iron. We need to figure out what the charge is. And then we want to look up what CrO4 is. It's chromate, and we can see that it has a -2 charge. So there's 1 of them and 1 of iron, so that means iron must be 2 as well. Here, potassium, ClO, that's the least number of oxygens in this chlorine group. Hypochlorite. Potassium is type 1. So we have potassium hypochlorite. Okay, I will briefly go over this, but it's fairly self-explanatory. Molecular compounds are when you have non-metal and non-metal. It's all in this group, and we're not dealing with ions here. We're just dealing with covalent compounds, which we will talk about in the future. But for now, you just need to know that these are molecules. They're bonded different than ionic compounds. The subscripts are not able to be predicted from the periodic table, so we need some way of naming them. What we do is we use prefixes. And so the first name of the element of the formula is named first. You give the full element name. The second element is named as though it were an anion, so we're adding "-ide". The number of the atoms present are denoted using prefixes. The prefix mono is never used for naming the first element. The best way to learn this is just to look at it in practice. P4O10 would be tetraphosphorus decoxide. And so what we're doing here is using prefixes. And so for 4 and 10, tetra is 4, and then 10 would be deca. And so tetraphosphorus decoxide. And so mono, di, tri, tetra, penta, hexa, hepta, octa. And then if we did it nona or deca, use those prefixes. And so here are the examples. These are pretty self-explanatory. When you look at it, you can see how it's named. So here are all the nitrogen compounds. You can't tell what the subscripts are going to be from their name, and so you have to use prefixes. So here, N2O, dinitrogen monoxide. But then here, look, if you have one nitrogen at the beginning, for some reason, it's just commonplace to not use that mono if it's first, so it would be nitrogen monoxide. NO2, nitrogen dioxide. So that's instead of mono. So the mono is not used if it's first. It is used if it's second. So something like CO is carbon monoxide. So the mono is used if it's second, not first. N2O3, dinitrogen trioxide. N2O4, dinitrogen tetroxide. N2O5, dinitrogen pentoxide. So here, give the name for AS2O5. It would be diarsenic pentoxide. Oxygen difluoride, OF2. Name these compounds. The first would be sulfur, because we don't use mono if it's first. Trioxide. Next is iodine trichloride. And this one is phosphorus pentabromide. So all I'm doing here is using prefixes and changing the ending to "ide." Carbon tetraiodide, Ci4. Phosphorus trichloride, PCl3. Dinitrogen trioxide, N2O3. Okay, so here is an overall flow chart for naming compounds. And this is where it's going to be tricky. Even the molecular ones can be tricky because you don't know how you're going to be naming it. And so if the first question that you're going to ask is there metal present? Is there anything from the left-hand side of the periodic table? If the answer is no, use prefixes. It's all nonmetals, just use the prefixes. Yes, then you have to ask, can it form more than one cation? If the answer is no, just use the element name for the cation. If it's yes, then these are the tricky ones. We have to determine the charge of the cation and use the Roman numeral after the element name for the cation. So here are the basics of nomenclature. I'm devoting the whole session to this because it can be tricky and I want us to do a lot of practice. And so go over practice worksheets and go over the notes. Let me know if you have any questions. I can always do extra videos if you have further questions on this material.